So we're going to end this last section here of Chapter 3 by taking a look at an interesting fact which very oftentimes shows up and becomes very, very useful. I know in my Calculus 1 and sometimes, or my Calculus 2 classes and sometimes in Calculus 3 classes that I teach, this fact shows up from time to time. So let's take a look at it. It's actually a very, very interesting limit. And what we have here is that the limit of 1 plus x to the power of 1 over x as x approaches 0 is actually the same thing as the limit of 1 plus 1 over n to the power of n as n goes to infinity. These limits are the same, and actually they equal the value of e. In fact, sometimes this is how the value of e is defined as opposed to the way that we defined it this semester. Well, let's take a look at exactly how this idea actually works here. So I'm going to start by going ahead and taking a look here at some different functions and then trying to understand how I can use that information to get to this limit. So let's suppose that I have a function here of f of x that's just equal to the natural log of x. If that's the case, then definitely very clearly, by what we've talked about in this section, the derivative of that function is just 1 over x. Now, we can actually state even more than that. So I'll say here, moreover, I could easily see that the value of 1 is going to be what happens when I go to my derivative and I plug in the value of 1. And I'm writing it in this order very purposefully, because there's another way that I could actually represent my derivative here. I could represent my derivative instead by using my definition of the derivative. So instead of using this shortcut formula, let me go ahead and show what it would look like if I said I wanted to calculate the derivative here and plug in the value of 1. I would have to have f of 1 plus h minus f of 1 all over h. Now, of course, that would mean that I'm going to be doing a limit as h approaches 0, and I can plug in 1 plus h and 1 into my actual function up here. So what that would look like is the natural log of 1 plus h minus the natural log of 1 all over h. Now the natural log of 1, remember, is just the value 0. And so I could rewrite this here actually one more time. So be the limit as h approaches 0. And I'm going to actually go ahead and rewrite my natural log of 1 plus h over here and write this over h kind of off on the side. And now I'm going to pull one additional final trick using properties of logarithms. Remember that we had a power rule for logarithms that said that we could take a power of the input and bring it down to the front. But we can also take things then in the reverse order. That is, I can take this coefficient of 1 over h and I can bring it up and make it a power of my inside. So if I was to do that, I would get 1 plus h raised to the power of 1 over h like this. Now you might be thinking, Kyle, this is a lot of work. Why exactly does this, or how does this relate to what I have up here? Well, what you'll notice is that this inner part, 1 plus h to the power of 1 over h, looks extremely similar to this first limit, except for the fact that I have a natural log. So here's what I'm going to go ahead and note here. First, I can see that this limit right here, according to everything that we showed, must be equal to the value of 1. And if this is the case, then we see that I could easily state that if I took e and I raised it to the power of this limit right here, so 1 plus h to the power of 1 over h, that would have to be equal to e raised to the power of 1 on this side, right? This would have to be true. So I'm just taking the same number here in blue and I'm making them exponents of the same value. So they have to be identical. But once I do this, I can go ahead and deduce a couple other things. So from this, I can see the right-hand side of this equal sign is obviously just the value e itself. And over here, I can start to use properties of continuous functions. Remember that we had rules that said, like, if I was ever doing a limit of a square root, I could change that into a square root of the limit. I could like move the limit past the square root. And we summarized back in our section in continuity that this was possible because the square root function was going to be a continuous function, and that we could actually do the same sort of manipulation as long as we had any continuous function. Well, e to the x, which is partially what I'm using here, is actually a continuous function. So I can slide this limit either up into the power or back out of the power. And I can do that kind of at will. So if I was to go ahead and do that here, notice that what I would end up with is a limit in front, and then I could just write e to the natural log of my 1 plus h to the 1 over h. So I'd have this limit is then equal to e. But of course, in the very last step, I'll notice that if I have e raised to a power of a natural log, since those are inverse functions, they kind of, quote-unquote, cancel out and really leave me with just my limit as h approaches 0 and my 1 plus 1 over h. Oops, sorry. The 1 over h isn't there. It's 1 plus h to the power of 1 over h. And that should be equal to e. How cool is that? Notice that what I have right here is actually this limit right over there. Now you might be asking, well, Kyle, how do you get to this limit right here? Well, notice that if we replace, say, my value of h with a value of 1 over n, then I can actually go ahead and see that we get the following. Notice I would see that I would have a limit of 1 plus 1 over n. Up here in the power, I would have 1 over n, which is just n. On the other side, the value wouldn't change. But notice here that originally, since h was going to 0, that would mean that I would need this value to go to 0, which can definitely be done if the value of n increases towards infinity. And here then is my first limit that I have, my second limit that I have right here. So both of these limits actually are the same and equal to the value of e. Again, this is a really kind of interesting fact that will be useful from time to time in all of your calculus courses.